Okay, so we will just get warmed up to dynamics today. Okay, we will not cover anything substantial. Today is a more of a philosophy course, because one really needs to understand uh, the role of dynamics in doing in robotics and in this computer control area. So, the first reason, the foremost reason why you need to do dynamics is to simulate robots, okay, and various kinds, whether it is manipulators or things which move around on the floor. You need to write the equations, and you need to write the equations because you want to evolve specifications for the actuators. You need to know how much power they need to have, what velocities they need to move at. You also want to compute the forces so you can design the links. This is more important for lightweight or flexible robots, because for the kind of robots which you have seen in the lab, they are very rigid and strong. So, they are not over designed, they are designed for stiffness, so that specifically in the control you do not need to do the dynamics. You can do kinematics, you generate the trajectories and then you just control it at the motor level. You do not need to worry about anything else down the line. So, that is the basic approach which you have. Then you get to this more complicated issue of designing control systems. So, to design control system, you essentially need to know what is called the structure of the dynamics. Is it first order, second order, higher order? If it is higher order, what are the contributions of the higher order modes? Okay. If you just do a PID, then will it interfere? Will it still be stable? If it is very complicated, then you have to cancel the higher order modes by using some mathematics or another simple model of it. So, in designing the control systems, you need the structure of the dynamics. So, there is a whole bunch of people in electrical engineering who sit and keep on doing structures. Okay. But conventionally, dynamics has not been computed in runtime in most common applications. You need to do it if you have a missile. Okay, if you consider that as a robot, because you are moving at very high velocities and you have to hit a target which is very small. So, you need to change things on the fly. That is why you pack in, that is why it costs $1 million, right, because you need to do the dynamics in real time, and as you go through all kinds of air and these kind of terrains. And this is built on top of kinematic analysis. So, now so we already know quite a bit of dynamics, right? You have done how many courses on dynamics? None? You have done lots of dynamics, right? You started in class 8 or class 9, right? You started writing force equations, mass moment equation, you kept on doing it, 8, 9, 10, 11, 12, first year, right, mechanics. So, you have had 5-6 years of dynamics. So, I was very happy with my dynamics until I became older. Okay. So, today we will just review some basic philosophies. Okay. And dynamics is a little bit more nebulous than kinematics. Okay. So, it is understood less well, and there are some issues here. So, today I will just try and look at some of the philosophies. Okay. This does not help you do any robotics, quote unquote, but so we all understand force equal to mass times acceleration, right, with a little cravat. What is the cravat? It has to be in an inertial frame, right? And what is the inertial frame? One in which f is equal to ma is valid. It's more complicated than that. In fact, so there's this quote from Sir Arthur Eddington, who said that basically what Newton says, that every particle continues in its state of rest or uniform motion in a straight line except insofar as it doesn't. Okay. So, there are so many exceptions to it, and if you think about it carefully, all your centripetal force, Coriolis force, centrifugal forces, they are all attempts at hacking F is equal to ma to make it work on system for which it is not designed for. Right? You know that in any frame which is rotating, you cannot write F is equal to ma, and to compensate for that, you create these artificial accelerations so that it fits. Okay. So, however, it is not such a bad thing. So, if you look at the first law, what is the first law? Newton had 3 laws, right? What was the first law? First, second and third, right? Yeah. Yeah. So, uniform motion unless acted upon by a force. So, but the real contribution of that law is that if we have a frame, okay, and where there is one free particle which is moving with a constant velocity, then all the free particles move with constant velocity, the same velocity. I mean, that is the real contribution of that law. Okay. The rest of it is arbitrary. I mean, it's there. I mean, you can write F is equal to mass times the accelerations. You could write F is equal to mass by 2 into acceleration, 2 times the acceleration. I mean, all of that is not important. Okay. And so essentially there is no definition in there. So, you are not creating something new knowledge, but except that he is saying that if there is a frame in which there is a free particle which is moving with a constant velocity, then all free particles must move with a constant velocity, which is something subtle and quite important. I am just stating it. And the second law, when you say force equal to mass times the acceleration, you are essentially stating that there is an entity called force which is independent of the mass it is acting on. So, you can take a force, you apply it to a mass 1 kilogram, you will get acceleration so much, but you can take that same force, apply it to another mass, and it will create twice the acceleration, but the force as an entity is a separate entity from mass or the reactions to it and the accelerations of the mass, so on and so forth. That is a fundamental statement, okay, that there is this concept called the force which is independent. And you know that if you have a spring, right, there is a force which is independent of the mass, it is simply coming out from material properties. Okay. Now, what happens is, because we start doing these things from school, right, and we kind of presume, we somehow we start using it without thinking about many of these things, it just settles in and we never question these things, that why is there something separate from force, or is it mass, and is mass and weight the same thing, like that you understand mass and weight are not the same. But similarly, the fact that force is an independent entity is not very well known. And then the third law essentially states that total momentum of an isolated system of particle is conserved, okay, but that is for forces of the push-pull type in which there is physical contact, pushing and pulling. If you have fields, then it becomes a little bit more complicated, okay, and that is why Maxwell's field laws are there. They are very different from Newton's law, particle laws. So, it is called there is this concept called physical laws and phenomenological laws. Okay. So, physical laws would be things which you can derive ab initio or prove ab initio, and then the phenomenological laws which says that, okay, I see this phenomenon, so this is the fit for that. Okay. So, I am welding, I use so much arc current, I am welding here, I use so much arc current, and I see this is the deposition rate, so I fit a curve through it. So, you can come out with a phenomenological law. So, the physical laws are a little different. So, essentially when you look at dynamics, you understand that there are these added things which you need to think very carefully about, forces, accelerations, what these laws do. But Newton was not isolated in what he was trying to do, and he is built on top of couple of other things, and then there is the famous Euler-Lagrange equation. Okay. Now, it is a interesting concept overall, where you start by saying that I have a fixed point A and a fixed point B on this trajectory on this xy plane. So, this curve C is a function, okay, of the equation type y is equal to y of x, but all of these curves belong to the type where it passes through A and B. Okay. So, fixed points. So, we define now a functional, okay. Later on we will define something called the action. I mean, it is just definitions, okay. These, its modern definition is a functional, function of a function, okay. So, you have this function which is y is equal to y of x, and if you look at this integral, okay, then you get this value, okay. Now, this integral has a value over this period, okay. There is no question of not being able to evaluate the integral over that period, you can sum the area under that, it has a definite value. Now, if you change the curve C, the value of the integral will change. So, you are now saying that there will be a class of curves, okay, depending on what is the exact functional that you define. Okay. Now, remember there is this function y is equal to f of x which is the path here. Now, you can define a functional which is a function of x, y, y prime, you can take couple of more terms here and there, you can define that. So, you are saying that there will be curves for which this value of I will be stationary, that means for small perturbations in that area the value of the curve will not change too much. Now, you are familiar with this overall concept because that indicates that it is a maxima or a minima, or it is a stationary point. Okay. In this case, we are more used to finding stationary point, a stationary value at a point. This is a stationary value of an integral over a interval, an integral of which kind, where there are the endpoints are fixed A and B. Okay. So, this is the interesting variation. Now, so if you call this stationary curve C bar and the equation of type y is equal to y bar, then this equation, this y is equal to y bar is given by the solution of this differential equation. Okay. So, this is the Euler-Lagrange equation. Okay. And so, you know about the Brunk-Stokrones problem, right? No, you know what is the problem? So, people pose this problem, I take a point A, I take a point B, right, and I create a path. So, I can either create a surface or I can put a wire through this, and I let this, so I put a bead, let us take a wire, right, I take a wire, so I put it on a path. So, I take a point, I take another point, and I say okay, I call this A, I call this B, I say okay fine, now I want to go from A to B. So, this is a free fall, I take a bead and I put it in and I let it fall, right, under gravity. So, ask this question, what will take the shortest amount of time to go from A to B? So, what is the most obvious answer? Straight line, right, and since it is so obvious, It's wrong. What is the next? Yes, circle. Why? Because it's the most beautiful shape in the world. It is symmetric. Huh? So it has to be arc of a circle of some kind. So what should be the arc? You can come out with, people came out with all kind of funny things. So you know what the answer is? Cycloid. Okay. So there are this Bernoulli brothers. You know about Bernoulli, right? They are not one Bernoulli. There is a generation of 4 generations of Bernoullis have bothered engineers all through their life. So 2 of them, okay, I think Johann and other is also a J. So they were the first to prove that it is a cycloid. So this is the problem. What is the shortest path? So now they did it through a different method. Okay, they directly perturbed, got a solution and perturbed it. The procedure is different. What this Euler-Bernoulli equation does, but if you look at a modern treatment of the same problem, you will find that people very simply define the use the Euler-Lagrange equation with the functional as the total time taken to go from path A in terms of the. So if you are given y is equal to y of x, you can define the slope at a point. So you know g is acting, so you know which component will act along the path. So it will accelerate, you write the equation at the point and you integrate it over ds and you get a functional. And so if you just solve this equation and out comes the equation of a cycloid. It's just brilliant. Okay, you can look it up. I mean, you can look it up in Wikipedia, okay, find lots of solutions. In fact, you are supposed to know it by the time you come down to your final year, pre-final year. If you don't, please complete your knowledge. And so by the way, if I give you 2 points on the plane, what is the shortest distance between them? Straight line. Can you prove it?
Yes.
How?
Triangle law. Triangle law.
How is the triangle law?
The distance between 2 points is the sum of, if A and B are the 2 lines of triangle, then the vector sum would be always less than the.
Well, that is built. That triangle law is in fact built on the fact the shortest distance between 2 points is a straight line. But anyway, you could just try this exercise. For that, the function is very easy to define, right? It is just integral ds, isn't it? You can define that. Just go back home today, take integral ds, apply this equation, right, and you solve it. You get y is equal to mx plus c, which is the equation of a straight line. So it's only after this that you can actually prove that the shortest distance between 2 points is a straight line. So this was a landmark in dynamics. So let's just go forward. So the next thing is I looked at only x, y. So I was looking at x and y, 2 coordinates, and so single dimension, this is the equation. You just go through and generalize. So if you have, instead of single variables, you have many variables, q1 to qn, and then you have q1 dot and q2 dots. Then you can break this up into n number of Euler-Lagrange equations of this kind. It's a simple extension, you can prove it, and the proof is there in mathematics through the what is called the calculus of variations. Right? Have you done a course in finite element? Anybody? 1, 2. You remember calculus of variations? Just a little bit. Something was done. Yeah, this calculation of variations without the Bronchi-Stockholm problem is lost. Okay, so you are actually trying to solve for a function or the path. Now comes the interesting part. Okay, now how is it related to dynamics? So, what you do then, you take this really silly combination of potential and kinetic energy. You say, I defined something called the Lagrangian L, and you say it is the kinetic energy minus the potential energy. Why do you say that? You do not know, right? You did thermodynamics, you know energy is conserved, enthalpy is conserved. What else is conserved? Enthalpy is decreasing, it cannot be conserved. Okay. I mean, all kinds of things are conserved, some are not conserved, some are monotonically decreasing. What they did, they just arbitrarily and rather took this combination T minus V, called it a Lagrangian, and it's okay, this is a functional, right. Well, you can define the kinetic energy and the potential energy without great, I mean, with difficulty, but you are supposed to be able to do that, end of 4th year in the IITs, and then you just write this equation. Okay. And that gives you dynamics. Okay. And dynamics for all systems, including holonomic, non-holonomic. Okay. For all systems, this will give you the dynamics. And you can show that if you write, if your coordinates, so these are generalized coordinates, right? This could be joint axis, it could be Cartesian, you can still write a Lagrangian, no problems about it. You can show that if you write this in Cartesian coordinates, then this equation becomes equivalent to mx double dot is equal to minus grad V. And since minus grad V is equal to force, you derive force is equal to mass times acceleration. So, the crucial thing is, see this you can prove from basics. So, this is arbitrary, L is equal to T minus V is arbitrary, right. What else is arbitrary? So, moment I talk about a functional, I am saying I have two fixed points, that is also arbitrary. That means if I am defining two fixed points and I define a functional, I need to know the values of the function that I am calculating, which is the time trajectory at 2 instants of time or something, or 2 positions. I exactly need to know where it is, sometime here and sometime there, otherwise I cannot do dynamics, okay, which is something you must keep in mind. Okay. So, question that usually we are asking, which is not explicit in the dynamics, is that when you derive dynamics, what you are asking is, I know that there was a particle which was here at some time, I know this is a particle which was here at some time, okay, or I know that this particle was here at this value x at some time, was there at this value y, x, x2 at some other time, and then given that these are the constraints on the system, okay, that it cannot move in a straight line, it has to move along this arc, there is a magnetic field acting, it is a magnetic particle and there is gravitational field acting. So, these are constraints. It says, you know, what is the possible path it could have followed, That is the question of dynamics. What is the possible path it could have followed? And so far, use of this funny things like, you know, L as T minus V, now note that 3 arrows. Why 3 arrows? Because this is a definition, okay, not equality, you are just defining this. Okay. So, that is something which you must remember and understand about dynamics. It is slightly less tangible than kinematics. Okay. And then essentially in the Cartesian system, this set of equation and f is equal to ma become identical. There is no difference between these equations. So, what are the pluses, what are the minuses? Okay. The pluses go like this. This one, the Euler-Lagrange equation deals with scalars, which is much nicer to work with, and then you know that if you want to calculate potential energy, you just need position. If you want to calculate kinetic energy, you just need velocity. Okay. Now, both of these are reasonably well behaved. Okay, they are reasonably well behaved terms. acceleration is slightly bad mannered. And why is it bad mannered? Because usually you always calculate accelerations to make it fit into Newton's laws, that is why you have a problem. Moment you have a rotating frame, you get this omega cross omega term, okay, omega squared, I mean omega cross Wirral terms and omega cross omega terms. Okay, so life gets messy. So my philosophical advice is, if you have to write the dynamics of a system and it is crucial, you do that first using Euler-Lagrange method, and then you go and you verify using the Newton-Euler method. And as you will see, usually computationally, well, there is pluses and minuses to both of them, it is faster to use the Newton-Euler method down the line, because there is a iterative algorithm which is more efficient in terms of number of multiplication, number of divisions, okay. And people spend their lifetime trying to find out how to save on 3 multiplication and 2 addition, and so Professor S.K. Saha is one of the specialists in writing a more efficient dynamics algorithm, right. So you go to him with a dynamics algorithm, it is okay. So 2 months later he will come up with another algorithm which has 2 less multiplications and 3 less additions, okay. So he specializes in that, I am more of a kinematician. So anyway, I find dynamics to be a little complicated because of these issues, okay. One needs to think about it. So let us think more about it. Now essentially Euler-Lagrange equation ends up it basically leads to Hamilton's principle also, okay. So in Hamilton's principle, here is the concept of the generalized momenta, okay, and then it is a little different. Now there is this another concept called the principle of least action or minimal action, okay. And so the basic phenomenon is that when we are perturbing, we are always perturbing, we are looking at solutions in the neighborhood where it is stationary. So we do not know, once we get a stationary value, whether it is globally stationary. So we get only local stability. So you find a solution which is like this, it is quite possible there might be another solution which is removed from this with no overlapping paths, which is also a stationary. So you do not know which one is the global optima, which is okay, we live with it, okay, because in the end you understand that you will end up with a differential equation which gives you some local properties. So and that has to be solved. So now what you can do is, you can define action as say between T1 and T2 of 2 times T dt, T is the kinetic energy, and then so as long as you stay with T out here, you end up with Hamilton's principle, but you can generalize this and you say, okay, why do I need to have time as the independent variable? If I know that this particle is going from some x to x1 to x2 and I want to find out what is the shortest path, I need another method. So you simply redefine this as integral r1 to r2 2t dt upon dt dr, okay, assuming r1 and r2 are fixed values. And now if you implement conservation of energy, T plus V is equal to constant, okay, so then you can show that the particle, so this is again dealing with particles in field, you can show that the path of the particle is one that yields a stationary value of this action value. So I mean the law of least action or minimal action is just a little removed from Hamilton's principle or Euler-Lagrange, well it still uses Euler-Lagrange, the basic functional approach, but if you do not have time as the independent parameter, then it is called essentially the principle of least action, minimal action, otherwise you go into essentially what is called Hamilton's principle. Now there is D'Alembert's principle. Now when people started moving from essentially particles to rigid bodies, they had other kinds of problems. The constraint set become different, and so basically what he ended up saying is that you take the forces acting on a system okay, and you take the time derivative of the moment of the system. So, if you add the two together, it will give you a vector. You find the component along any consistent virtual displacement. So, if there is a particle here and this is supposed to be moving in a circular track, particle moving in a circular track, it is here, then the only consistent virtual displacement is tangential. So, if you take the sum of all the forces and you dot it along with this, okay, then you get 0. That was his fundamental principle. D'Alembert, he says, okay, now if you do this, unproven, no proof exists for this. So, then you apply, you get the Lagrangian form of this, and it says that you take the applied forces plus you take the inertia forces. So, if you know the accelerations, you apply in the opposite direction to that. We have now termed them the inertia forces. Then we get the same Lagrangian equations back, okay, for the rigid body. Now, if you use Hamilton's method, which is using the generalized momenta, then you land up with essentially n, you land up with 2n first order equations. If you use Lagrange's method, you get n second order equations. And fundamentally, if any of you use MATLAB for any kind of simulation, you know that you have to break things down into first order equations for it to work on MATLAB. Okay, for Runge-Kutta, for example, works on first order equations. If you have a second order equations, you go to break it up into two first order equations by defining a derivative. Okay, so if you have typically an equation like mx double dot is equal to f and f is given, then what you need to do is you got to write, you got to define two variables x1 and x2, and you define x2 is equal to x1 dot. Okay. So, then you write this equation as mx2 dot is equal to f, and you simply solve for it and you will get x1 values, which then give you the x values. So, this is what you have to do in MATLAB, okay. And for most other simulation, the direct solution of second order equations numerical is dicey. So, that is why Hamilton's method is quite appropriate, and lots of physics people who actually solve very, very complicated systems, they essentially go down to Hamilton's method. Okay. Our systems are actually simpler, robotic systems are simpler. So, physics is a much more complicated system and they use a lot of Hamilton's stuff. So, finally, to end up the philosophy lecture, since you are wondering, why is it that, I am taking away all the dynamics you have learned. So, have you heard about these kind of court cases? Huh? Creationism versus Darwinism. Okay. So, there is a lot of stuff which said that fact that God created is a valid model also. Like if Lagrange can say you take t minus v, Bible can also say God created man, and then you just take it as that in his own image and you just follow through. So, there is a lot of these axioms. So, they say if you teach that, why don't you teach this in the school as valid curriculum? So, they, and in fact they continued, but this is a historical judgment in 1982, which is very interesting. So, it says a scientific theory is something which is guided by natural law. We are okay with it. The purpose of science is to explain nature. It has to be explanatory by reference to natural law. Okay, so, you explain it by referring to various phenomena in nature. It is testable against the empirical world. So, if you say that heavier bodies fall faster, then the famous Torricelli experiment, right, in which dropped a ball and a feather in a vacuum chamber at the same time and they both fell down at the same time. So, it must be testable, I mean, in the empirical world. So, all of that is something which we understand. The next two are really fantastic. Okay. Take time and read it, right? You have read it? So, it says its conclusions are tentative, okay, and not necessarily the final word. And the final one, it is falsifiable. So, you wrote F is equal to ma and all these things, but you know that in relativity it does not work. In fact, the statement Newton's law is a classic one. It says F is equal to ma in an inertial frame. So, he is saying that if you do not have inertial frame, this is falsifiable. Similarly, if you look at Lagrange, he says T minus V, I mean, and then, but he says if the whole purpose is, if the particle goes from here to here and there is no need to minimize or to find stationary versions of T minus V, all of dynamics goes for a toss, but Lagrange is okay with it. Okay. So, these two parts is something which I as a end to this thing in dynamics, where I am telling you is that most of the dynamics that you have learned is tentative, right, and is based on conjectures and theories which seem to work, and we are able to make cell phones and all kinds of things using the same laws. Okay. We need to understand that somewhere down in the middle, that all the science and theory that we know is actually tentative and it is falsifiable, and over a period of history we have changed the theories, and so also these theories might change. If you are really lucky, they will change in your lifetime. Okay. So, if you are less lucky, they will change after your lifetime. Okay. Why is it luckier if you change in your lifetime? Yeah, then you can get many gadgets. There was actually a proof once which saying that if you have a, what is a condenser? It is a variable capacitor which was used to tune radios in the past. Somebody has actually proved that if the condenser size is less than 1.5 inch or something, then you will be unable to tune. Okay, but there was one idiot who did not know that law, and he just made a smaller one and it worked. Okay, so there is new theory after that. So we need to keep this in mind, and dynamics is not very difficult in robots. You can pretty much work through that, and we will just, and it's there in every book. It's given identical in every book, okay, with small variations. For example, Professor Saha's book is has this additional things about how to write very fast algorithms. So, you are sometimes interested in it, sometimes not interested in it, and the original plan was that we would get him to take some of these lectures in dynamics, because it is always better to hear it from a specialist. Unfortunately, he has a class exactly on the same slot, so we couldn't do it. So, you will get it from a non-specialist. Okay. So, we will see now, and so it is mostly computational. You have to just write equations and then either write F is equal to ma in vector form. So, the real difficulty there is calculating accelerations, the rest is trivial, and the other form is quite easy. It is just systematic, and you can take partial derivatives, and now you have Mathematica and all these tools. So, it is very efficient writing it either way, and my focus will be to quickly be able to do the dynamics and then focus on some aspects of control, because that is quite important in the curriculum. Okay, so we will stop here, and tomorrow we will do some real stuff.